Let's get started. So today we are going to cover the details about the programming for the balancing car for the first time. And this project will last for at least 4 weeks. And you guys need to let me know, send me an email who are on the same team. So 2 people per team. Okay. And that's one thing for the tutorial. Another one is for the microcontroller class. We'll talk about this on Friday as well. So on Monday next week, in the microcontroller class, starting from 11:15 a.m., we are going to have a webinar. There's a guest speaker who is a pioneer of IC design back in 1970s, who is a friend of mine, and he's going to talk about how he made the first microcontroller in 1970s. So please attend that webinar. You can ask questions. So the link is provided on the website. Check out the link on microcontroller's website and prepare for some questions. Right? I have funding for pizza, but just in case, because everybody's picking up the pieces from the same box, so probably I don't want to do that. Right. So let's get back to the tutorial. So there are 2 parts of the tutorial, and before we add the wireless module to the car, so you have watched this video, and the purpose or the goal for the first phase, the phase 1 of this one, is to let the 2-wheel car get balanced by itself on the table, right? So get this done first and demonstrate that to me, so you'll get at least, I think, 60% of the credit. Do not wait until the last minute to start working on this. It's not an easy project, okay? And you need to demonstrate me it is able to stand on the table, and also after you push it, it is able to balance itself to adjust the position. I have a new set point for the car. And also it should be able to carry something. You can put a water bottle on the top or anything. That's how I want to demonstrate that to me. And it should be a PCB board, but not everything being wired on the breadboard. So you just need a 1 microcontroller. It can be a Uno, can be a Nano, and 1 MPU sensor, position sensor, and driver as well. But everything should be integrated on 1 PCB, but not 2, not 3. 1 PCB for the car itself, and another PCB for the joystick remote controller. Okay? So definitely you know that the joystick also need a microcontroller with it, because it's talking to the wireless module. So make sure you have 1 piece of PCB for the remote controller, another PCB for the car itself. Okay, so that's the goal. After you are clear with the goal for phase 1 of the project, let's look at the details of the design. Okay, starting from part 1. Okay, I think we can start talking about the accelerometer first. But I think maybe some of you have a question regarding the wireless module, the 2.4 gigahertz Open Smart. So let's look at that one first. So what are the pins available for that module? So that's from homework 3, and that's the Open Smart 24 gigahertz wireless module. And here is your 328p MCU, definitely RX-TX, and that's your 2.4 gigahertz wireless module. So that's a antenna on the PCB RX-TX, and here So signal is being sent from a master to the slave. So it's going to this module wirelessly. And it just simply connect this one to here. Oh no, sorry. TX to RX, right? And then RX to TX. So the master is going to send the command to this OpenSmart 2.4 gigahertz module, and it's going to directly convert that serial type of data to this module through the 2.4 gigahertz wireless signal. And after this guy received that signal, it's going to send that one to RX, to the MCU on the slave side. And definitely you want to connect this one, but if you don't do that, which is fine because there's no data being sent from this MCU to this module. And so that's the connection. And you really don't need to understand the protocol of the communication because it's not necessary. It's probably going to take like 3 weeks to just learn the protocol itself. But the goal here is to get it done. We need a car, a product to be sold, right? So we don't want to take too much time to look at all the pulses and timing diagram of the protocol. So let's just connect everything according to the hardware diagram I have on the tutorial. And definitely this MCU is going to control the stepper motor, and also you probably want to debug your circuit by connecting this guy to your computer through serial. That's a serial monitor. And this one definitely, because that's you need a controller, which is a joystick. So whenever this one is receiving that joystick's signal, that's an analog input, right? You still remember that? So the joystick is simply a, what kind of actuator? Is that potentiometer? So it's providing a voltage output, which has an analog input for the MCU. And ADC in the MCU will detect that voltage change and convert it into a digital data range. So what's the range for the digital? 0 to 1023, right? Okay. So you can use that number as the input and then control the stepper motor on the slave side. So that's how that works for here. I haven't implemented this, but by looking at the data sheet, so to send the command from here directly to this module, you just simply use serial dot print, whatever. You can print the string or you can print a variable, an integer. I think they're going to work. So that's for this MCU. What about this one? So like I said, because everything has been integrated in the sensor, you don't need to worry about the protocol. So whenever the signal is being sent to this guy, it's going to receive it because there's no switch in the air. You couldn't just like cut the signal, the wireless signal in the air. So it's going to be received by this antenna and will be directly converted to a serial data type and then being received by this guy. But however, before you take the data from the buffer, it will wait there for the customer to grab it from the variable and use it somewhere else. So you probably need an if statement in your slave and say if serial dot available. Okay, so whenever this guy is true, yeah. If you don't say anything, that means when this one is true, have a curly bracket and then do something. So you can directly transfer the data to a variable, let's say data, and you assign serial dot read. So here's a function you can directly use, right? So serial dot read. So you can read the data in the buffer being stored in the buffer to this data, so you can use it for whatever to control the stepper motor. Did you try this? Does this work? It works. Okay. So don't think this too complicated. It's not that complicated since everything has been designed by engineers. And you want to be a computer engineer in the future, so you are going to design the details in the future, but not right now. Let's just use it, get a product developed, and make it work. I think just one direction because there are only two directions for the stepper motor, clockwise or counterclockwise. Since you don't want the car to jump, right, or fly. It couldn't fly. Yeah. Okay. And I saw James. So he used the soft serial. Have you ever used soft serial? Because all these communication protocols, if you have used, I think I mentioned the I2C, soft I2C or soft SPI, you can literally just look at the timing diagram of the protocol, and whenever, so what's the start condition for I2C? You still remember that? A quick quiz question. So you pull SDL low before you pull SCL low, I guess. So so that's the starting condition. And when you want to stop the communication, you pull SCL high first and then pull SDA high. Or vice versa. I forgot, but there's a starting condition. So you can program everything in software by yourself by looking at the timing diagram. You just pull it down, just do a digital write, assign a digital low, and delay for 2 milliseconds, and then pull the SCL low. But for serial, you just follow their protocol, do whatever is required by the timing diagram for serial. However, again, you don't need to do it because everything's in the library. You just download the soft serial from GitHub and just use it. So you can assign any digital pin on the microcontroller instead of using the TX and RX pin, which is a hardware hardware serial, right? Because maybe you are using that two pins for some other purposes. So by using the software serial, you can use any digital pin for serial communication as RX and TX. All right. So that's for the wireless module. Hopefully you can make it work as soon as possible. When is it due? Friday. I had made one extension. I don't want to make another one. Okay. Get it done. Hopefully. And again, so I mentioned this in the morning for group 1 for my controllers. So do not stay up too late for just working on homework assignments. Start working on any homework assignments as early as possible so you are not fighting for the last minute. It's lack of sleep really affect your immune system. That's true. I have experienced something like this when I was in graduate school. And the professor, one of the professors, in my first year, I changed to another professor because of that. It's too hard. And he asked me to report to him every day at 4 p.m. So I have to make progress every day, every single day. So during that month, I worked until 3 a.m. pretty much every day and sleep for 4 hours and start working again and report to him at 4 p.m. That lasted for about a month. And I can feel I was weak, and I was not sick, but I feel I probably will get sick really, really soon. That's really bad, But that's how you can get productive sometimes and So in 6 months, I start from knowing nothing about the topic and get a journal paper published in 6 months because of that. That's bad for health. Not recommended. So during the pandemic, do not stay up too late. Right? Okay. So starting from the MPU sensors of the car. Okay. Balancing car. So remember the first one. There are totally 6 data lines from the MPU sensor. So 3 acceleration lines, X, Y, Z, and 3 gyroscope data lines. And there's a configuration a register, but let's take a look at the data register first. So they are ACC EL X out and ACC EL Y out and ACC EL Z out. For the accelerations for the 3 axes, X, Y, and Z. And do you still remember how many bytes for each one? For each register, for each axis. 16 bytes. Yeah. So 1 byte for each. So every register has a higher A bit and a lower A bit. I have to combine them together. Do you still remember that line, the command to combine them? Just simply do an OR logic. Do I have that here? Yeah, this one, right? This line will do the job. So it starts reading the data from 3B. How many binary bits for 3B? How many binary bits? Come on, do you still need to calculate it? 3B hex. How many binary bits? No, hex. 8. So what is 3? Yeah. What is B? 11, right? So it's going to be 8 plus 3. So 1011. So starting from 3B, so the one after that is 3C. So 3B is a 8-bit memory, which will store the higher byte of the x-axis acceleration data. And there's another 8-bit register, which is 3C. It's going to store the lower 8-bit acceleration data, and we combine them together to make them one data bank, right? So that's the acceleration data you want to use. So that's how to do it. Use the wire, which is I2C's class. So wire dot write. So write this address to the MPU sensor, and then end the transmission. So the MPU knows what's the address the master is going to request for data, and you want to stop the I2C communication every time for every conversation, right? And then start again. So after this one, it's going to send another request, which is going to be 2 bytes. So now it makes sense because 2 bytes, which has the higher and lower byte for the acceleration data together. So request for 2 bytes and just do a I2C read following that. So the first one will be the higher byte and being shifted by 8 bits to the left. Okay, and then simply do a OR logic, just OR it. You'll get the lower byte combined to the acceleration X data. So that's how you get the 16-bit acceleration data for the X-axis only. Okay, let's do the same thing for the other 2 axes, Y and Z. then you are done for the acceleration collection. And for gyroscope, it's very similar, but the calculation can be a little bit different. But the way how you read all these bytes will be the same. Here's one more thing. So what's the address for the MPU? So what's the address? Can you tell from here? What's the address? 6A, right? So you are getting a 6A because the LSB is 0. Is it 0? Is the LSB 0 for this byte, for this 16 byte? Yeah. So the LSB here is controlled by the hardware connection. So which is the 80 pin on your MPU. So you need to ground it to get the LSB to be 0. So you are using 68 instead of 69 as an address. Okay. I will start at homework 3. Yeah, I know you're done. Yeah. So hopefully this will be a really easy one for you in the future, since we are going to use this a lot. It's a very popular accelerometer on the market. So here's a register map, right? So starting from 3B and 3C will be the lower byte from 0 to 7. And combine them, you get the acceleration in the x-axis. And here's a really quick demonstration for the gyroscope reading. So the gyroscope inside the chip measures the angular velocity. So if you do not do anything to the sensor after you connect everything to the pins and just put on the table like what I'm doing here, so are you expecting any data in the serial monitor? So again, the gyroscope measures the angular velocity. If it's not rotating, are you getting anything? No. So that makes sense. You're getting zeros. I didn't zoom in. If you zoom in, you'll see an offset for the gyroscope, which you have to subtract from every single reading in your PID controller. Keep in mind, that's important. Looks like they are 0, but they are not. Okay? I didn't zoom in. I couldn't zoom in the serial monitor. If you zoom in, you'll see that error here. Just to let you know ahead. Okay. So that's the gyroscope reading, and also every time you power up the car, it's going to start collecting the gyroscope data. Because your hands will shake, and if you hold it perpendicular to the table, and you do want to average out the first 500 readings. It doesn't have to be 500, it can be 300, 400, 1,000, doesn't matter. So 500 can be a good number of data points to get an average. So you hold it perpendicular to the table, and you have to plug in this piece of code in the setup function or loop function. This is the question for you. Setup function, why? Yeah, you don't want to calibrate average all the time in the loop. So in the setup function, get an average, and you're done. You get average value. So that's going to be the offset for whatever you hold it. You think it's perpendicular to the table, but actually it's not, right? So there will be some wobbling there, and there will be a offset. So you get that value and subtract that value from every single reading in the loop. So use a for loop to accumulate all these readings, the 500 readings, really quickly. So get the data, and then divide that value by 500. You get an average. Yeah. So that's going to be the calibration value or the offset. So PID controller, we learned it in junior design. So the theory of it is pretty simple, just three equations. And let's focus on how to implement it. There are a lot of tricks by doing that. So if you look at the the equations, you can see that there's a dt, okay? dt. So what is the dt in your microcontroller? What's the dt? Between data points. That's correct. But if you want to make it more intuitive, it is actually the time it takes to run the program, because it's a discrete system. It's not continuous, and every time it has to rerun, get back to the front of the code to sample the gyroscope data for once. So the next time it runs, it's going to sample the gyroscope data. It has to be another loop. So the dt will be the time it takes to run the loop for once, right? But here's the issue here, because the loop will run forever, but the setup function is going to be executed in front of the loop for once. So what's a way to subtract that time, and what are the functions you can use in IDE to get a dt? Yeah, so look at this one. This is pretty interesting. So I probably should draw this for you. The PID controller. So P definitely is Kp, right, which is a constant for the P variable, times the error, and I is Ki, and integration from 0 to t et dt, and d is Kd times det over dt. So we are trying to define the dt right now in the code. And it's called loop time. Which is a dt. How to figure out the loop time? So we know that the setup function and the void function, the loop function, will run forever. And here will be the dt. But nothing here will be counted as dt, right? Because this will be only executed for once, and after that is done, it's going to run this for every sampling. And let's see, new page. So if we define, because it depends on, there might be many factors, like the capacitance and changes of the environment or any other issues may give you a different loop time if you do not define a certain loop time in your code. Or sometimes the sensor is not responding in a timely manner, so it takes more time. So we'll change your DT over time, which is really bad for the PID controller, because you really need a constant delta T. So the way to do that is, let's just pick up a pretty safe DT. I know the loop probably only takes, for example, 3 milliseconds. Let's say 3 milliseconds, plus minus 100 microseconds. I don't know, okay? So if I pick up a safe DT, let's say 4 milliseconds, I know no matter what happens, it won't be longer than 4 milliseconds, okay? So I will directly set up everything to be 4 milliseconds. Then I'll be more comfortable. I know it's going to be 4 milliseconds forever, so it's not going to be changed anymore. Okay, so that's a really good idea. That's what I learned from other people. And in order to do that, how do you want to make a 4 milliseconds fixed in your loop function? Delay, yeah, or a while loop. Whenever it's not satisfying the condition, just holding there, do nothing. Whenever the condition is satisfied, do whatever after that. Okay, either way. So let's look at the details about how to implement this. So we have a void set up. I don't care what are these ones. They will be executed really quickly and do all these setups and declarations. And at the end of the setup function, I will write a line like this: loop timer, so that's a variable, integer, equals to microsecond, micro s, so that's a function in your IDE, plus 4,000. And so let's write down the microseconds definition for this function. So microsecond, so that function is a timer begins when the board is powered up. All right, given that, is this a variable or constant? Whatever this function is going to return. Is that a variable? So is this going to return a variable or constant? So look at the definition. It's a timer. Definitely it's a variable, right? So it's going to return the time since the board is powered up to your whatever variable whenever you request it. Okay. So when we are adding 4,000 to it, since we know we are trying to set up the loop time to be 4 milliseconds, so 4,000, what's the unit for this guy? Microseconds, right? So 4,000 microseconds being added to this function, because the unit here is going to be microseconds. So if I invoke this microsecond parenthesis, this function over here as the end of the setup function, so what is the time being returned over here? Just look at this line, nothing else, okay? The setup function. If I request the time here, so is the time will be the time has been spent since the starting of the setup function or somewhere else? Yeah, from here. Okay, so you record it here in this line at the end of the setup function, record it, and add a 4,000 microseconds to it, and assign everything to this variable. And now let's finish the loop. So the two lines in the loop function, I will explain to you why we want to do this. So at the end of the loop function, do this: while microsecond is less than loop timer, then do nothing, because I don't have anything after that. So do nothing, just a semicolon. You can have an empty curly bracket, but it's not necessary, just taking space. So if this do nothing, whenever this condition is not being satisfied anymore, jump to the second line, which is loop timer. So loop timer equals to loop timer plus 4,000, right? Now let's look at this, if this is making sense. If this is doing the job, Okay, after you know how to set up the loop time, this can be used anywhere. All right? Think about it. Probably it's hard to understand for now if I don't draw a diagram. Think about it. So, for example, the first time you power up the board, so it's going to run this setup function until here. So the loop timer is going to record definitely the time since you powered up the board. It's the time spent here, plus 4,000 microseconds. So it actually set up a standard for the loop time after the very last line in the setup function. So you can think about this, okay? So at the end of setup function, you just directly add 4,000 microseconds, boom, to here. Okay, I know your loop function probably won't take that long, probably here, but you set up 4,000 microseconds to here. Whenever it's not being satisfied, just wait until this is satisfied. Then add another variable here, which happens here. Look at this. So this will add 4,000 microseconds to the end of the loop function. And because this is a variable, we're still talking about the first time the loop function is being executed. The first time, keep in mind, the first time. So whenever the microsecond function is less than the loop timer, what is the loop timer here? The standard, the longest time, right? Because I use the microseconds here, which is a variable, add 4,000 microseconds, which is the desired loop time. So I directly add it to this variable. Whenever this one, which is keep changing, is not here yet, then do not do anything after it. So just wait until it is satisfied, which means how much time has been taken by this program, by the loop, right? Yeah, by the loop. It's been 4,000 microseconds for the loop. And then do this. Why do we want to do this here? After this. Huh? Because after the first time, it's going to come back to the top of the loop and check this again. But every time you have to increase the variable by 4,000 microseconds because this loop takes 4,000 microseconds. So you can keep comparing that to the microseconds. This is a variable. It's keep adding time to this variable over time. So this has to be changed. Is there a place to reset it? I didn't see that. I think so. Yeah, it's pretty long. So check the data sheet. That's a really good question. Check the data sheet. See what's the overflow time for this one. At least a couple hours. Okay. Is that clear? Any questions? No? Great. So that's how you define the loop time for the PID controller, which is DT. Right? And then the angle for the car. Number 4, I guess. So that's a cross-sectional view of the car, right? For example, it leans forward to here. That's a really big angle. I don't think your PID controller can handle that. Just trying to draw it so you understand what's going on. And the way you want to plug in your MPU sensor is you want to solder. Let me show you from the side. You want to solder the pins perpendicular to the board. Let's see if I have it here. oh, here, like this. Okay, so that's a breadboard. That's a cross-sectional view. And you plug in perpendicular to the board when you're testing. Okay, and here's X, here's Y, and coming out from the monitor will be Z, right? And the gravity will pointing down because that's the board. So if you do not do anything, just place the sensor on the board, you are going to read the acceleration in the X direction to be what? So what's the acceleration in the X direction? Come on. You have, yeah, so do we have acceleration for now? I think you do, right? G, 1G. So you are going to read 1G for this direction. Because it has a MEMS, a macro mechanical electrical sensor inside. So definitely gravity will make that macro structure falling a little bit. So that's why it's going to sense that 1G, right? So that's why if you don't do anything, like what I'm doing here, this is an example code you can try. I didn't shake it, right? I just placed the sensor on the board, and it's going to read 8,000 something. Why is 8,000? 500, something like that. That's 1G, and because it's defined by the digital system inside the sensor, it's A192 LSBs per G. Since it's 1G, so you are reading something close to it. It's not exactly 8,192 because it's not really super perpendicular to the board. It can be a little bit forward or backward. So, but I can tell it's pretty close. So that's 1G. But for the other two directions, it should be 0. Right? Is that 0? It should be 0. So test it and see if you can get 0 in the Z and Y direction. But for X, you are getting 1G. Okay. So that's what I tried. Okay, for the angles, let's look at this. So that's X, and that's Z. Okay, that's how you plug in your sensor to the board. And that's Z, that's X. Okay. So this one, this will be dz delta z. Pretty simple, just do a subtraction from the reading. And what is this? What is this? What's the acceleration in the x-axis? So that's a table surface. What's the acceleration here? 1g. Is that 1g? That's 1g. So what's the angle here? So it's going to be a sine because that's what I exaggerated this, right? So definitely the angle won't be that huge. So you are probably, there will be something like this. So your PID controller can still save it. It's too large to save. So in that case, so this line will be pretty small, will be tiny. So we can treat this function as, so theta equals to a sine acceleration x or z? Z, right? ACCELZ over 1G. However, this function is going to return the readings. This is in readings. So you have to convert it into degrees after this. So the value, in your code, you probably want to write down something like this: a sign, and definitely float, it's a fractional number. ACCELZ, and over what? Over 1G, which is 8,192 LSBs. 0.0, don't forget that, to have a precision for data. And that's the A sign, which is in radians, and you want to convert into degrees. How? Or 360 over 2 pi, right? Same thing. Okay, so we can convert everything to degrees. So this one equals to what? 362 over 2 pi is definitely 180 over pi. This equals to 57.296. Okay, so you can see in the code, there's a constant like this, so you understand where this comes from right now. Right? Let me see if there's something else I got to cover. All right, so here we know the angle from the accelerometer. Definitely you can calculate the angle from this one. And there's so we still have we also have the gyroscope in the maps chip. So we can also get an angle from there, and then we're going to do a data fusion for these two data points. And after we received the acceleration data and convert it into an angle data here, we need to, so that's still in LSBs, in binary. So we probably want to convert it to degrees. The way to do that is, so it's going to be blah, 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 LSBs. So that's the data, right? And wait, that's acceleration, but now the gyroscope. I think I skipped something from there. Take a look. Yeah, here. So the acceleration data is done. We're done with that one. Okay, the gyroscope data. The configuration register is fs underscore SEL. There are several options. If we pick up this one, definitely you just need to send a specific configuration to this register. So I have it here, I guess. Where's the configuration? But in a sketch somewhere, okay? So this I have a lot of examples for this configuration. It's pretty simple, just one line to set up the sensor. Use this unit, the first row, and the full range will be plus minus 250 degrees per second. So degrees per second from this unit, you know it's going to be angular velocity, right? Degrees per second, angular velocity. That's for the gyroscope. And you set up the precision or the range to be the first one, and you have to use this number to convert the binary data into a degree per second data. Okay. So if we implement this in your sketch, so definitely whenever you acquire the data from the variable, you are getting how many LSBs? Is that correct? The binary data is the binary data, and it's just how many ones or how many LSBs. And this data has to be, you have to multiply this data by which number first, right? And then divide everything by the LSB precision, which is here. So 131 LSB per degree per second. So we're converting the binary readout to the degree data. So look at units. That's how we configure the register in the MPU sensor, right? So that's a binary reading, the 16 bits you combined together. And that's how many LSBs. And times what? So finally you can get a degree. Yeah, how many seconds? So how many seconds? 3. So it's going to be 0.004 seconds, 4 milliseconds, right? So 0.004 seconds, because this will be cancel, 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 cancel. So only degree is left. So the result will be blah, 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 how many degrees. All right, so that's how you convert your gyroscope readout to a real degree data. So that's for the gyroscope. However, after that, we still need to combine the gyroscope data with the acceleration data to get a real angle in real time for the car. I mean, there might be a lot of questions for that. So I tested. You don't have to do the data fusion, but there might be some flaws if you don't do that. So everybody suggests that you should do the data fusion. So this line actually, it's a high pass filter for the gyroscope data and low pass filter for the acceleration data. We have to test for longer time to verify this really helps a lot. But for now, if you really want the car to stand on the table, you don't have to do this. But let's do it since it's just one line, pretty simple. So the very last point I want to make sure you understand that. So if you look at this line, okay, it's keep accumulating the gyroscope, the angle changes for the car, and where this comes from. So actually here, so you use the 0.004 over 131, so you are getting that 0.000031. Okay, so when you are looking at the numbers, you are not puzzled, right? Because everything is calculated. So until here, I think you just need to verify in the video showing me when you move the car, change the angle, you should be able to show the angle in real time in the serial monitor. Okay? All right, that's everything for today. We'll cover more next Monday. Oh, Friday, actually. Okay. Thanks.